All right, welcome back, everybody. We're going to work on finishing chapter 5. We left off at the section of the chapter called Collecting Gas Over Water. So, a common experimental technique is to have a reaction. Let's see here. Your reaction over here is going to be zinc and hydrochloric acid reacting to form hydrogen gas. Now, you want to collect that. And so, what you do is you bubble it into a system. You have water there. And what happens is slowly the gas will push the water out of the chamber and you will get this nice collection of gas above the water. The reason a lot of people get these calculations wrong is because they don't account for the fact that above the water when you're collecting your gas, so here you can see both hydrogen molecules, but also water molecules. So water will escape with the gas you're collecting and be above the water there. So you have to factor that out. And so this is going to depend heavily on what's known as the vapor pressure of water. And vapor pressure is, well, in second semester when you study equilibrium more, you're going to end up with an equilibrium here where gas molecules are entering the gas phase and also then re-entering the liquid phase at the same speed. So that's an equilibrium. So the total concentration of water in gas phase doesn't change, but the molecules are going into gas phase and out of gas phase at the same speed, and so you'll have that equilibrium. Once you reach that equilibrium, the pressure of the water vapor above the fluid, that is your vapor pressure of the water. So we're just going to look at a calculation here. So at elevated temperature, sodium chlorate decomposes to produce sodium chloride and oxygen gas. Let's see, 0.8765 grams of impure sodium chlorate. So we don't know how much sodium chlorate is actually in the sample, heated until the production of oxygen gas ceased. So you imagine oxygen's bubbling into a water system, and you start to collect gas above the water. Let's see, the oxygen collected occupies 57.2 milliliters at the temperature of 22 Celsius and a pressure of 734 torr. What is the mass percent of the sodium chloride? Wait, sodium chloride. Oh, no, hang on. Yeah. Okay. Sodium chloride is one of the products. I just skipped a line. So the mass percentage of the sodium chlorate in the original impure sample. We're given the vapor pressure of water at 22 Celsius. All right. So we're being asked for. Okay. So let's see our mass of impure sodium chlorate, 0.8765 grams. Let's see. Am I going to meet any of those? Oh, yeah. Okay. So, uh, okay, you've done a lot of calculations so far where you calculate molar mass. So now we're at the point where we can put these molar masses up in our known values so we don't have to do extra calculations. 106.44 grams per mole. Okay. Volume of the O2 is 57.2 milliliters. Temperature 22 Celsius. So that pressure you're given is total pressure of the system. And that's 734 torr. Pressure or vapor pressure of H2O, it's 19.8 torr. All right. Now we can start solving. So the first thing we need is our chemical reaction. This is a decomposition reaction. And if you read the problem, it tells you what it looks like. So you have your sodium chlorate. Now that's going to be solid. It is going to decompose into sodium chloride and O2 gas. You look at this and you go, well, that's not balanced. So if you balance it, you're going to get 2, 2, and 3. And really, it's best just to kind of look at the oxygens there, because you say, well, I have 3 here and 2 here. So let's make those meet at 6, and then everything else balances out pretty easy. So you're going to need this. Now, you have to take into account that oxygen and water vapor are mixed together. So I have to factor out the water vapor. So what is the partial pressure of O2? So we know by Dalton's law, we have this. So we can find the pressure of O2, at least taking our total pressure minus the partial pressure of water, or in this case, water's vapor pressure. So it's going to be 734 torr minus 19.8 torr. That is going to be 714 torr. Now, this is the step here that a lot of people miss when they get these problems wrong. They're not factoring out the water vapor that's a part of the system. Okay, so the thing we're going to need is how much. So, what is the actual mass of the pure sodium chlorate in the original sample? Okay, so we can do that. We have a pressure of O2. We have everything dealing with O2. So what I can do is say, well, I can find moles of O2. Okay, so remember our partial pressure gas equations. You get pressure of O2 in volume equals moles of O2 and then RT. Well, we know R is going to be in atmospheres. We have torr. And it's going to be in kelvins, and we have Celsius. So let's go ahead and change those. 714 torr. 760 torr per atmosphere. And this is going to give us 0.939 atmospheres of O2. Our temperature, that is going to be 22 degrees Celsius plus 273 is going to be 295 Kelvin. Okay, so we're looking for specifically moles of O2. So if we rearrange our gas equation, partial pressure of O2 times volume over RT. And now we can plug in numbers. Okay, so R 0.08206 liters atmospheres or moles kelvins. Our temperature is 295 Kelvin. And then our partial pressure of O2, which we figured out up here, zero 0.939 atmospheres. Okay, and let's see, our volume is 57.2 milliliters, so that's going to be 0.0572 liters. When we calculate this, we're going to get 2.22 times 10 to the negative third moles of O2. Now from here, we can just do a simple calculation like we've been doing. to find the mass of sodium chlorate. Okay, so 2.22. Did I write that wrong? No, looks like it's fine. Okay, so we're going to have 2.22. It kind of looks like the proportionality symbol. Times 10 to the negative third moles of O2. Okay, so now we go back up to our chemical equation, and we see we have 3 moles of O2 to 2 moles of sodium chlorate. Okay, and then we use the molar mass we put into our known values, which is 106.44 grams of sodium chlorate per mole. And this is going to come out to be 0.158 grams of sodium chlorate. Now, our mass percentage, that's going to be our mass, ClO3 over the mass of the sample times 100. Okay, so that's going to be 0.158 over 0.8765 times 100. And we find out that our original sample was 18% sodium chlorate. So go back and make sure you take account of how we factored out the water vapor that would be in the gas with the O2. That's the real key part to solving problems properly for this type of experiment. Okay, now the kinetic molecular theory of gases. This is where the ideal gas law actually comes from. So the first thing you want to imagine is gas molecules in a container. It's a cubic container, sides of length L, and they're all just bouncing around, bouncing off walls, all kinds of stuff. So in the first image here, you can see a bunch of molecules just kind of bouncing around. In the second one, you can see the path of an individual molecule. And because this is a three-dimensional container, our molecules are moving. So two ways to look at this. If we have our X, Y, Z axis, and we say that a molecule is going on some path arbitrarily into space, and then it's going to have, and we're going to locate it. Like this. And so our molecule is right here. And so what it has on it is it has unit vectors for its velocity. So we're going to say that this is its velocity vector, and it has unit vectors on it of Vz, and then Vy, and well, just the best I can, and Vx. So it's going to have these three components on it. Now, because neither I nor you want to spend an entire week doing vector math just to finish this chapter, we're only going to worry about one dimension. So we're only going to worry about the x direction. But just know in general, particles are moving in 3 dimensions. And a lot of times you have to you have to keep that in mind. If any of you take physical chemistry with me, we will do that. Okay, so we are only going to focus on the x direction. So that means we're going to focus on Vx. So V, of course, again, it's velocity. Your textbook uses U for velocity. I don't like that. I use V, but however you're comfortable. Okay, so we're imagining a particle. You see at first it's going in the negative V. So, okay, another thing. We need to set positives and negatives. Okay, so plus X is in that direction. So if it's going the other way, it's going negative X. So you see that it's going in the negative V direction in the first part. It's going to bounce that, hit that wall, bounce. Then it's going to be going in the positive V direction. It's going to hit that wall and then come back. We're worried about a full cycle. We're worried about once it hits here, how far does it have to go to go from here and back? Okay, so a couple things we want to keep in mind. Those of you who haven't done physics, I'll just give you definitions. Momentum is P, and that's going to be mass times velocity. Now, what we're worried about is change in momentum. So that's going to be, we have the room there. That is going to be the final minus the initial. Okay, now our change in velocity, you can see. So our MV final is right here. So that's just going to be positive MVF minus our MV initial is right here. And so that's going to be M times, oh, hang on, not F, X. This is going to be negative MVX. So we're going to get MVX minus MVX, MV plus MV, and that's going to give us 2 mass times velocity. Okay, so like I said, this particle is going to hit the wall. It's going to go all the way across, hit the other wall, come back, hit the first wall again. That's what we're worried about. We want to know the path it has to take to reach that first wall again. And so you notice it hits here, it goes L, then it come back to hit the wall again, it goes L. So it's the distance it's traveling is 2L. Okay, so we have another definition from physics. Velocity is a change in position over change in time. And you'll be happy we're going to leave it in discrete math because technically your velocity is a time differential of position, but we're just going to do it the discrete way. Okay, so I want to know how long it takes. So I'm going to use a little algebra, and I'm going to get change in x over Vx. Now, we talked about that change in x. That change in x is change in position. It goes from here to here, so 1L, here to here, 2L. So change in x is 2L. Okay. Now, we're going to get to a big definition. Newton's second law of motion. Most of you have probably heard this as F equals mass times acceleration, force equals mass times acceleration. There's one that we use quite a bit more often where it's force is change in momentum over change in time. And what we have is we have change in momentum and we have change in time. Okay, so this is going to be 2 mvx over 2L over Vx. Okay, so we're going to take that denominator and flip it and multiply. So we're going to have 2 mvx multiplied by Vx over 2L. And what we're going to get is our force is going to be m Vx squared over L. Now, all these particles in this gas are identical. The path they travel is identical. But they're very probably moving at different velocities. So that indicates as you get used to physics, you find out these different velocities means each one of these particles is in a different energy state. So for n particles, our force, our constant m over L is going to pull out, and then we're going to have our sum of I equals particle 1 to particle n of Vix squared. So we have to sum together the velocities of all of these particles. And then we want to know what our average velocity is going to be. So then, of course, you take the sum and divide by the number of particles. Okay, so I'm going to rearrange this. My sum is going to equal n times the average squared. And so that means that my force now is going to be m over L in Vx squared, or m in number of particles over L average velocity squared. Now, something else we wouldn't really do until like 400 level chemistry. You can do these derivations multiple times, and you'll see by symmetry, Vx squared equals Vy squared equals Vz squared. Okay, now let's see. Okay, I'll just show you this, but we talked about that vector, that velocity vector. So your particle is just going off in any direction. It has x, y, and z components. The magnitude of that velocity vector, just how big is it? Is the square root of each component squared added together. So you can imagine then that my average velocity squared is going to be Vx squared plus Vy squared plus Vz squared. I just squared both sides and got rid of the square root. And then remember we said that Vx squared, Vy squared, and Vz squared equal each other by symmetry. That means that now you're going to have Vx squared plus Vx squared plus Vx squared, or 3 Vx squared. So then we're going to want to get Vx squared to be 1/3, dividing by 3 of the velocity squared. Because see, here's the thing. Everything right now is in terms of Vx. We want a generalized solution in terms of just the average velocity of a particle or a gas molecule. All right, so now I'm going to take this expression for force and substitute in my new expression for Vx squared. Okay, so now force is going to be m times n over L times 1/3. Why do I keep doing that? Average velocity squared. So now we have everything in terms of a velocity that can be going in any random direction, which is a much more general solution, which is what you're after in physics. So now we're going to have mass times the number of molecules over 3L average velocity squared. Okay, so let's look at the concept of pressure. Let's see, where do I switch into? Oh, right there. Okay, I'm having to look at my notes because I was going to do this earlier, but then I saw in the chapter that they did this later, so I moved it. And so now I'm like flipping through and my notes are out of order. So bear with me. Actually, I'm going to write this in a different color so it stands out, or look, because we're looking at a new section here. We're looking for a definition of pressure. Let's see. So what do we know pressure is? Basic definition. Pressure is force per unit area. Well, when that so it's a cubic box. So go back up and look. It's a cubic box, so area. So we're thinking of the area of that wall, which we know this side is L, this side is L. So the area of that wall has to be L squared. Okay, so we have force. All right, so we're going to get force is going to be m times n v squared over 3L. And then, of course, my area is L squared. Okay, well, that's not very fun. Okay, so that's going to be m n average velocity squared over 3L times 1 over L squared. This is going to be mnv squared over 3L cubed. And I hope you realize that in this cubic box, L cubed is volume. Okay, so now our pressure is mass, number of molecules, average velocity squared over 3 times the volume of the chamber. Now we're getting closer. So now we're going to have PV equals m n v over 3, or 1/3 mass of your molecule, number of your molecules, average velocity of a molecule squared. Okay, well, we're getting close because you notice we've gotten PV to pop out of this. Okay, so let's see here. Okay, so the first thing I want to take note of is I want to look at an expression for kinetic energy. Okay, kinetic energy is the energy of a moving object. Okay, so our kinetic energy, the expression in physics, is 1/2 mv squared. Now look here, I can rearrange this to pull a 1/2 mv squared out. So first off, if I want to pull a 1/2 out of 1/3, what do I have? 1/3, that actually equals 2/3 times 1/2. Okay, so PV is going to be 2/3 N, and then I'll have 1/2 mv squared. Okay, so that's 2/3 N times the kinetic energy. Now, I think this is where I need to skip down a few slides. Wasn't quite sure how long it would take me to do that. Now, we need to think of, now we can get a new definition for kinetic energy in terms of temperature. And so kinetic energy in terms of temperature is 3/2 kBT. KB is what is called your Boltzmann constant. We don't really need to know the number of that right now, but that's what it is. This is from Boltzmann statistical mechanics. And so, and then what you see here, this is some new notation for you. These brackets, this indicates an average value. So an average value or an average energy of your system. It's that's more quantum mechanical notation, but that's what that means. Okay, so now we're interested in this expression of kinetic energy in terms of temperature. Again, we could derive this, but that would require me to take you through at least calculus 3, and you would need to understand, we would need to walk through the math of what's known as a Boltzmann distribution to get this. So right now, I hope you take my word for it that your kinetic energy in terms of temperature is 3/2 kBT. Okay, so I go back up. I did leave myself too much room there, didn't I? Okay, so if I have PV equals 2/3 in kinetic energy, then I'm going to come down here and I'm going to substitute in this for my kinetic energy. I'm going to get PV equals 2/3 in 3/2 kBT. Okay, so 2/3 times 3/2 cancels out. And so PV just equals N kBT. Well, all the time it's looking more and more like our ideal gas law. Now, N is our number, so it's our number of molecules. And we've been doing calculations going from molecules to moles. Okay, so our moles to molecules. And we use Avogadro's number. So of course you remember Avogadro's number is moles, and -1 is its unit. N is molecules. So my number, So you remember N is going to be molecules divided by molecules per mole. That's going to give me moles. But that means that N is going to be N over Avogadro's number. Or number of molecules is going to be number of moles times Avogadro's number. Okay, so now I can substitute that. PV is going to be number of moles, Avogadro's number, KB, T. And now we're at a place where we have another factor come in. It's this NAKB. NAKB is in fact Avogadro's number times the Boltzmann constant equals R. So once we realize that through advanced thermal chemistry, we have PV equals N RT, and we have our ideal gas law. Okay, so kind of a fun little derivation, or maybe not. I guess it just depends on how you feel about it. And so now we understand a little bit more about the math involved. We can look at something known as root mean square velocity, which is going to be the average velocity that a gas molecule is moving inside of a chamber at a given temperature. And so again, your book uses U, I like to use V, but your root mean square, and the reason it's called root mean square is because look here, it's the mean or average mean value of your velocity squared the square root of the whole thing. Root, let's see, root mean square. Okay, so that's going to be the square root of 3RT over M. Now, in this case, the R you're going to be using for these kind of calculations is 8.3145 joules per Kelvin times mole. Joules is your energy value. So that's the unit for energy. So like kinetic energy would be in joules. So anytime you're working with thermodynamics or you need energy calculations or you're doing your velocity, your velocity or rates for your your molecules moving in a gas, you're going to use your R equals 8.314 joules per Kelvin times moles. So then so then the question is, well, we've been looking at some stuff. How would we get here? Okay, well, we know one expression for kinetic energy is 1/2 mv squared. Another expression, as we talked about, is 3/2 kBT. Okay, well, they're both kinetic energy. So we say, and then we say, well, what would these be per mole? Okay, well, if we want them per mole, because this would be joules, this would be joules. So if we want them per mole, we have to multiply by Avogadro's number. Okay. This one is going to become interesting because this is going to become 3/2 NAKB T. And you remember NAKB is R, so this becomes 3/2 RT. So your kinetic energy becomes 3/2 RT when you have a mole of your gas molecules. For a single molecule, you use Boltzmann constant KB. Okay, so these are both kinetic energy, so we have got to be equal to each other. 1/2 Avogadro's number, mass, velocity squared equals 3/2 RT. We're going to get rid of the 1/2, the 3/2 by multiplying through by 2. And AMV squared equals 3RT. V squared, or average velocity squared, is 3RT over NA times M. Now, what is that? Okay, so NA, remember, has units of moles. M has units of grams. So Na times M has units of grams per mole. That's our molar mass. Okay, so then I'm just going to square root both sides. And so when I square root both sides, my VRMS is going to be 3RT over, and Na times M is our molar mass, square root. So remember that exponent of 1/2 is the same thing as square root. So this really just comes with setting the two versions of kinetic energy equal to each other, making sure that they're in terms of their molar values. Okay, so we're actually going to use the concept of root mean square here. You have a 100-liter flask containing a mixture of methane and argon gases at 25 Celsius. The mass of argon is 228 grams, and the mole fraction of methane is 0.650. Calculate the total kinetic energy of the gaseous mixture. Okay. We want total kinetic energy. Okay, so mass of argon, 328 grams. Okay, so argon itself, I look at the periodic table, and it's 39.95 grams per mole. Our temperature, 25 degrees Celsius, which remember, this problem didn't have to tell you 25 Celsius. It could have told you standard conditions. That is the temperature for standard conditions. Our mole fraction of methane is 0.650. And this is an energy calculation, so our R is, 8.3145 joules per Kelvin times moles. Okay, so automatically I can see that my temperature and gas constant don't match. So temperature is going to be 298 Kelvin. And so the thing is we know that our expression for average kinetic energy is 3/2 RT. Total kinetic energy would be the average kinetic energy multiplied by the total moles of gas molecules in the system. So that's what we need. We need total moles of gas molecules. Okay, so let's think about how we do that. Well, I know that my mole fraction, okay, so total moles of CH4 plus moles of argon. And since it's the mole fraction of methane, that means moles of methane has to be on the top. But I can get a number for moles of argon because I remember I have 228 grams of argon. And that is going to be 39.95 grams of argon per mole. And that is going to give me 5.71 moles of argon. Okay. Now for fun, we're going to rearrange this algebraically before we plug any numbers in. So I'm going to multiply through by the denominator. So all right, factor through. All right, then I'm going to get argon by itself and CH4 by itself. Okay, so that's going to be chi CH4 times NCH4 minus NCH4 because I brought this in over to this side. Then I'm going to take this chi times N of argon over here minus okay. Now, if I get rid of the negative sign here, that's going to flip these on this side. Minus chi NCH4 equals chi CH4 N of argon. All right, then I'm going to factor out number of moles of methane. That's going to be 1 minus chi. Then I'm going to divide through. I'm going to get moles of CH4. That's going to be mole fraction of CH4, moles of argon, over 1 minus, and I can plug numbers in here. Okay, so moles of CH4 then. Okay, so our mole fraction, 0.650. Moles of argon is 5.71 moles over 1 minus 0.650. And when you multiply this out, you are going to get 10.6 moles of CH4. Now I have the moles of argon in the chamber. I have the moles of CH4 in the chamber. And so I remind myself that my average kinetic energy is 3 halves RT in my molar value. Now my total kinetic energy is going to be total number of moles multiplied by my average, which is going to be total number of moles times 3 halves RT, or 3 halves in total RT. And I can plug numbers into this. Kinetic energy going to be 3 halves. Total moles is 10.6 moles. So methane plus 5.71 moles for argon. R is 8.3145 joules per Kelvin times mole. And temperature is 298 Kelvin. So my total kinetic energy is going to be 6.06 times 10 to the fourth joules, or as we commonly do in physics, we change this to 60.6 kilojoules. Now, I say we commonly do that. If the problem doesn't explicitly tell you to do that, you can leave it in joules. You won't get it marked wrong. But there's a little energetic math for you on systems of moving molecules. Okay, so let's talk about effusion versus diffusion. So effusion is, so imagine you have a chamber. The two sides are blocked off. One side is a vacuum. There's nothing there. The other side has gas in it. Effusion is the movement of the gas through a small opening into an evacuated chamber. So how fast does it do that? We have something called Graham's law of effusion, which is rate of gas 1 over rate of gas 2 equals the square root of the molar mass of gas 2 over the square root of the molar mass of gas 1. So you have your rates of 1 over 2, and on the other side, you have your molar masses of 2 over 1. So that's a way you can remember it. And the way I think it looks, so your book has this. I think a good way to remember it is here, where you have your VRMS1 over VRMS2, because we've just been working with VRMS. So if you were given these rates, uh, or you were given like the speeds of your molecules, you would know where to put them. Diffusion is the mixing of two gases that were originally separated. So again, how fast does that happen? And again, you can analyze that using Graham's law of effusion. So let's look here. The rate of effusion of a particular gas was measured and found to be 24.0 milliliters per minute. Under the same conditions, the rate of effusion of pure methane gas was 47.8 milliliters per minute. What is the molar mass of the unknown gas? Okay, so I called it molar mass 2. Uh, I did that because if you look here, molar mass 2 is already in the numerator, so I'm not going to have to do extra steps in math. So you could have named it molar mass 1, just as long as you make your ones and twos line up. So I called it molar mass 2. Now I know that VRMS 2, so that's the unknown or the particular gas, is 24.0 milliliters per minute. VRMS of methane, 47.8 milliliters per minute. Let's see. CH4, the molar mass is 16.04 grams per mole. And we should be fine. Okay. All right, so let's start with our Graham's law. So my one is methane. So I have V RMS of methane over E RMS, or whatever the other gas is, so gas 2. That's going to be molar mass of 2 goes on top. And then on bottom, we're going to have the molar mass of methane, square root. You see my square roots are horrible. That's why I use the brackets with the 1/2. Now let's square both sides. How much space is? Okay, so I'm just going to flip these. One half, same thing as square root. I'll square that side. square that side. So the square on the left side is going to get rid of the square roots in the top and the bottom because when you have a square, it goes to that one and it goes to that one. Same thing, that one will go there and it will go there. Okay, so that's going to give me my molar mass of gas 2 over the molar mass of methane. Going to equal VRMS of methane squared over the VRMS of gas 2 squared. So then I solve molar mass 2 by multiplying through my denominator. That is going to give me VRMS methane squared times the molar mass of methane, which I put in my known values, over V squared RMS for gas 2. And I have all these numbers. So when I plug these in, that's going to give me 47.8 squared. Let's see, methane is 16.04 grams per mole. And like I said, you can just start putting actual molar masses into your nose instead of calculating them each time. And then over 24.0 squared. So the molar mass of gas 2 is 63.6 grams per mole. Now, you could take this, do a little bit of research, and you could actually identify what the gas is. Okay. So we're going to end the chapter looking at some real gases. So real gases, of course, deviate from ideal gases. The lower the pressure and higher the temperature, the closer they get to ideal behavior. The graph on the right here is purely for, I can't see that, nitrogen gas. But one of the reasons this happens is because we've been talking about volumes that a gas is in, but we haven't talked about the individual volumes of each gas molecule. Okay, well, the gas molecules have volumes, and we have to account for that. So if you look at the left, what you see is gases going further and further away. So it's like you see uh, your N2 deviates just a little bit versus your CO2 deviates from your ideal gas line quite a bit. They're quite a bit different. And so what you're looking at is not only the volume of each individual molecule, but we also have to take into account what's called van der Waals forces and other intermolecular forces, which will also cause a gas to deviate, because intermolecular forces are electrostatic forces of attraction and repulsion between gas molecules. So PV over nRT is called the compressibility of a gas. How tightly can you press all the molecules together? And you see here at very low pressures, the compressibility of your gases goes below ideal gas, meaning that you can compress the molecules together much more than an ideal gas. At your higher pressures, these gases shoot way above an ideal gas, so you can't compress them as much. Now you see a point there where some of the gases recross the ideal gas line, so they're each going to have a pressure where their individual their volumes and then their individual um, intermolecular forces are going to zero each other out, and they will momentarily reach that ideal gas behavior again. And so you notice if we look at the right, the lower the temperature, the low temperatures are deviating from the ideal gas, and they get closer to ideal gas as temperature increases to a certain point. Well, that's because at lower temperatures, your molecules have a lot less energy in them, and so they're moving much, much slower, which means the intermolecular forces between them are much more influential. And the same thing, you see them shoot off away from ideal gas at high temperatures. Again, high temperature, tons of energy in your molecules. And so the kinetic energy is going to far outweigh the intermolecular forces. And so, it, well, that's not a good way to put it. But anyway, tons of energy in that system. And so you're, once again, your compressibility becomes much lower. There's too much energy in the system. So what experimentalists ended up finding, working with theorists, is that a correction needed to be made. And so if we change the ideal gas law to P equals nRT over V, the first change they make is to account for the volumes of the individual molecules in a gas. And so that's going to be P prime. That's going to be nRT minus N times B, or nRT over V minus N times B. So the volume of your container minus, so you have to subtract off a given volume of your molecules. N is the number of moles of gas in the system, and B is a factor that you can find by getting experimental data, fitting an equation to the graph, which some of you do in lab. This is one of the reasons you do it. And then B is going to be unique to the individual gas you're using. So you fit your equation and you'll know what B is. Your van der Waals forces. You can have electrostatic attraction between positive and negative. You can have electrostatic repulsions between positive. You can have electrostatic repulsions between negative and negative. Now, what that's going to affect is your concentration term. And so what you have to think about is inside your gas, you have a certain number of molecules that are being pulled by van der Waals forces, and that's going to be dictated by concentration N over V. Then you have a certain number of molecules that are doing the pulling, and that's also going to be dictated by N over V, which leads to N over V squared. That's where that comes from. And then again, it's a proportionality. So you find that your correction to your concentration term has a proportionality constant of A, which again, you would look that up and it's going to be unique to the gas that you're studying. And what that ends up leading us to is we have a new observed pressure for our gas with our volume correction and our van der Waals correction. And then we can move that around to what is known as the van der Waals gas equation. And so this is the gas equation we would use. It's technically in PV equals nRT format. This is our new gas law for non-ideal gases or real gases. Okay, I'm not really going to make you work with that in assignments. I want you to know it exists, like kind of run through your head what the terms mean, why they're there. But this ends chapter 5 for us. All right, so we're going to be starting chapter 6, which is going to be thermochemistry. So thermochemistry is going to be a little more math intensive, so just kind of hang on for the ride. All right, I'll talk to you later.